Hello everyone, we are Group 5 and the title of our group project is Flight Delay Prediction. This project aims to predict flight departure delays by using historical flight data. For dataset, flight delay and cancellation dataset contains historical flight information from 2019 to 2023. The dataset, which comes from Kaggle, allows us to study flight performance, identity patterns in delays and cancellations, and build prediction models.
Hello, Doctor. I will briefly present our work regarding data cleaning, feature engineering, and the preliminary data analysis. The data cleaning phase, we removed non-predictive or redundant data, specifically regarding departure delay. For classification tasks, we removed this field entirely to prevent leakage. For regression tasks, we retained it, only use the data from non-cancelled flights. In terms of feature engineering, we transform raw data into meaningful predictors. We extracted months to capture seasonal patterns and the day a week for weekly travel trends. We applied warehouse encoding to categorical variables and standardized numerical features to accommodate algorithms sensitive to data scale. Finally, we get datasets for modeling. Also get some key data insights based on the processed data. We observed several interesting patterns, include airline performance comparison, seasonal trend analysis, and overall distribution patterns of delays.
For Model 1, the task is to predict the risk of flight cancellation. This is a binary classification problem, and one important constraint is that we only use information available before departure, so the model reflects a realistic prediction scenario rather than hindsight analysis. In terms of methodology, there are three main steps. First is the feature selection. We removed all post-event variables such as actual delays and arrival outcomes to avoid information leakage and ensure the model only learns from per-departure signals. Second is data splitting. Instead of using random splitting, we applied a time-based split, which better stimulates how the model would be used for future flights. Third is a modeling strategy. We evaluate multiple models, including logistic, regression, random forest, and XGB, and focused on ranking-based metrics, since the cancellation events are highly imbalanced. On the right, the table summarizes the quantitative performances of each model using ROC and AOC, average precision, and lift over the based cancellation rate. From this comparison, we can already see that XGB constantly outperforms the other models, which leads to the visualization and the deeper analysis shown on the next slide. Now let's look at the results. On the left, we compare the models using ROC curves and precision recall curves. From the ROC curves, XGB performs the best and has the highest AUC. This shows that it can better separate cancelled flights from non-cancelled ones. The precision recall curves are more important here because the cancellations are rare. Although the curves are unstable at very low recall levels, XGB keeps higher precision for most of the range. This means that it can focus cancellations into the high-risk group more effectively. On the right, we show the results of parameter tuning. The validation AUC values are grouped close around 0.7. This shows that model is stable and not based on single lucky result. To conclude, XGB gives the best and most stable performances among all models. It's suitable for flight cancellation risk assignment before departure, where the goal is risk ranking, not direct decisions.
Model 2 Flight Delay Prediction First, for feature selection, we engineered a comprehensive set of predictors. These include temporal and root features, as well as categorical encodings and historical aggregation features to capture past trends. Second, to ensure our model flags real-world forecasting, we used time-based date splitting. Regarding our modeling strategy, we choose four models: linear regression, random forest, XGBoost, and LightGBM. From the table, we can see LightGBM had the higher R-square score out of the baseline models. To achieve better model performance, we also tried model tuning. The tuning comparison showed that XGBoost achieves the best performance in RMSE and R-square metrics, indicating that it outperforms other models in terms of overall error control and variance interpretation.
This slide summarizes our main conclusion. Overall, Simplicity achieved the best performance in both flag cancellation and deleted proceeded outperforms the baseless models. This is merely because gradient boosting effective at capture low Guanyar and temperature sense in flag data. However, the positive power is still limited due to missing features such as weather and air traffic. In-feature work incorporating richer data sources and team series models could feature improve performance.